What would happen tomorrow if your credit card is stolen and your money is siphoned? What would happen if your password for net banking is hacked by someone? What would happen if your personal data is leaked by an unknown source? Bad, isn't it? But don't worry, I have got some good news for you. Soon we are approaching a time when everything will be highly secured and there is no chance of hacking or any unethical activity. That is the power of quantum computing, and that is the subject of today's video: quantum computing and how quantum computer helps us securing your future. I can tell you this much, this is going to be a super interesting video, and I would request you not to skip, because this is going to make you go into certain computing technologies which possibly you don't know, and some of the cutting edge technologies which are going to shape the artificial intelligence and possibly our near future. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the video on all about quantum computing. So first, as we do, let us quickly look into what are the topics we are covering. So first we would know what is quantum computing called, what is a quantum computer, how a quantum computer operates, what are the claims made by Google and IBM, the two, I would say, IT giants, how have we achieved quantum supremacy at all, what are the features of classical and quantum computer, how a classical and a quantum computer operates, what is the little bit brief history of quantum computers, difference between classical and quantum computer, quantum superposition, a very unique feature and how it helps in quantum computing, and also quantum entanglement and how it facilitates quantum computing. So this is going to be a very interesting video where we are going to understand the details which is going on right now all over the world, and in the meantime we will also learn a little bit about the underlying principles of quantum mechanics. Okay, so where do we first go? First, let us understand what is quantum computing. Now, quantum computing is basically an area of computer science that we can call that uses the principles of quantum theory. And quantum theory explains the behavior of energy and particles on the atomic and subatomic levels. Hence, quantum computing uses those subatomic particles such as electron or photons, and quantum bits or qubits allow these particles to exist in some more than one state, and what is that we are going to look soon. So what we can say is that quantum computing actually uses the underlying principles and mathematics of quantum mechanics. It helps us in solving problems which today's computer cannot do. I mean to say, even the supercomputers possibly are unable to solve, or it would take an infinite long time to do those. We can also say this famous saying that light bulb isn't just a better candle, but is something completely different. Now, what I'm trying to tell you is that this is something revolutionary. We have never watched anything such as quantum computing, and this is going to change the entire perspective in which we look into computer technology and the process of computing. So we can say quantum computing is a new approach to calculation that uses the principles of fundamental physics to solve extremely complex problems. And we can also say that some of the quantum system it is used to model include photosynthesis, superconductivity, and some of the complex modular formations like caffeine, etc. So now that we have seen overall what is quantum computing, and we understand that it is a kind of a computation method which uses the underlying principles of quantum mechanics. Now, does that mean that we pick up the electrons and photons and neutrons and we put inside a computer and do that? Let us find it in the next part of our video, and we will see that what actually are quantum computers. So quantum computers are basically something which is based on quantum computing. Quantum computers are machines that use the properties of quantum physics to store data and perform calculations. This can be extremely advantageous for certain tasks where they could vastly outperform even our best supercomputers. Classical computers, which include smartphones and laptops, I would say, encode information in binary bits that can be either 0 or 1. But in a quantum computer, the basic unit of memory is qubit. We will look more into that. Quantum computers operate in qubits. And remember that it is 158 million times faster than the most sophisticated supercomputer we have. And that's a huge in number. Right? So that is something really fascinating. And quantum computers are, due to the current hitting is so hot that we have to keep it almost to absolute zero, that is minus 270.15 something degrees Celsius. Now you note that this was an ideal case when our laptops, our mainframes or our desktops were being developed. If you remember, I belong to those days when we were operating in MS-DOS 6.0 and we were told that we need to keep the desktop in a nice cool place, otherwise the heating might create error, bugs and problems. So this is the nascent stage of quantum computing, when the things are stored at minus 270 degrees Celsius. But I'm sure that a time is going to come when we can operate quantum computers just like the way we do today in desktop or laptop. Now, apart from these features that I told you about quantum computing, there are certain very important facts, fascinating facts I'm sure you're going to enjoy. The first thing that I started the video is that quantum computers can solve problems that are impossible or would take traditional computers impractical amount of time. So what happens is that virtually unbreakable encryption will take place, and quantum computers will change the landscape of data security, even though quantum computers would be able to crack many of today's encryption techniques, predictions that they would create a hack-proof, I would say, replacements. How it would create a hack-proof system based on quantum superposition, we will look in the later part. So also one thing, some people think that classical computers are actually better in performing than quantum computers like email, spreadsheets and desktop applications. But the intent of quantum computers to be different, a tool to solve problems, doesn't mean that it would replace classical computers. Classical computers would continue, but quantum computers would do weather connection, weather forecasting, PNP or certain other very difficult problems. Quantum computers are great for solving optimization problems. So Google announced it has a quantum computer that is 100 million times faster than the classical computer, and the processor is called a Sycamore processor. It is based on transmon superconducting qubits, where the conventional chips that we use are 2D readout wires taking more than half the area. Sycamore is a totally re-engineered chip. The qubit area chip is in fact a two-dimension, however it is stacked on the control chip. The specific design that makes Sycamore more scalable than its counterparts is called flip chip design. Now, in order to, as we are talking, that in order to keep computers, quantum computers stable, they need to be cold, and that is why the inside of D-Wave systems computer is around minus 460 degrees Fahrenheit. Now, if you're wondering what is D-Wave computer system, actually D-Wave Quantum System Incorporation is a Canadian computing company based at Burn Bay, British Columbia, and D-Wave was the first world's company to sell computers to exploit the quantum effect of their operation. We also know that according to the principles of quantum mechanics, there is something which is called superpositions, and superposition is actually the term describe the quantum state where particles can exist in multiple states at the same time, which allows quantum computers to look more different at different variables, and it will get more enhanced speed. How we will definitely prove and look into this video. It is also that rather than more electricity, quantum computers will reduce power consumption anywhere between 100 up to 1000 times, because here we use something which is called quantum tunneling. And as you see, the top computers can still manage everything. A 5 of 20 quantum computers will be surpassed within 50 qubits to attain supremacy. Even though quantum computer is so, it grows in exponential growth. So yes, we have a kind of a 50 qubit will attain supremacy all that point. However, IBM researchers said that using their own methods, they could be able to create a supercomputer to handle at the same task in only 2.5 days. So I mean to say, this is something really great, that 50 qubits quantum computer will actually solve a lot of things. Okay, so the thing is that what we understood from here is that quantum computers are great. They are very fast and they have certain features. The Sycamore processor is one of Google's quantum computer that they claim, and these are the relevant features using the principles of quantum mechanics. But the question lies that where from actually the quantum computer evolution started. What was the brainchild? Was that a person or any kind of a debate that actually invoked the idea of using quantum computer? Coming up in the next part of our video. Okay, there's something which is called a quantum supremacy, and there has been claims made by these two giants, Google and IBM. Now, actually, quantum supremacy is basically a kind of a goal demonstrating that a programmable quantum device can solve certain things which I would say no classical computers can. Now, classical computers means those we are talking, those who have got laptops, desktops which calculate in bits 0 and 1. Now, quantum supremacy means actually a way of developing quantum computers that has a super polynomial speed over the best known or possible classical algorithm for that task. Then given a kind of a task, I would say it would outnumber the current highest possible supercomputer mainframe which no possible classical algorithm do, and it will have a super polynomial speed. Okay, so here is a little bit of history that in 2019, the CEO of Google, announced that it has achieved quantum supremacy. Now, what do we mean by quantum supremacy? That they have got a computer where a specific mathematical problem, I'm not going into that, can complete a calculation in just 3 minutes 20 seconds. Now, which generally the computer, I'm speaking of October 2019, as I remember. During that time, IBM had a supercomputer which was called Summit, and they claimed that IBM supercomputer will take around 10,000 years for that problem to solve. So here is a news cutting which tells that IBM researchers actually dismissed completely that idea. So I mean to say, they told that no, this is absolutely rubbish. So they said that they will use their own methods. I mean to say, they would be able to program a supercomputer to handle the same task in only 2.5 days. Forget about 10,000. So they faulted Google for assuming that the supercomputer is limited by the amount of data it can store in system memory, and said to the internet company that they have failed to account a plentiful disk storage that could overcome the limitation. So this was, the world was taken by a storm, and everything was happening, something that we have achieved quantum supremacy. Google was claiming that this mathematical problem can be solved in this, whereas IBM was, and that was basically the culmination. That was the trigger, I mean to say, through which things happened, through which the entire idea of quantum computer came in. So it is quite worth noting. Now, before we go further, one thing would be very important for us to understand, that what is a classical computer. Until we understand that, how will we understand that what is a quantum computer, and we won't be able to understand how these two are different, that is white and the dark, right? The light and the darkness, and then only possibly we can appreciate the power of quantum computer, coming up in this part of the video. Okay, so if we take any old desktop, or if we take any laptop, even if we take a mainframe supercomputer and a series of computer, all we have to understand and we have to keep it in mind is that these are all programmed to carry out sequences of arithmetic or logical operations automatically. That means they need to compute something. They are given a set of instructions called programming or algorithm, and we give a problem in order to solve that. Now see, the rules of this, including the mobile that you're using, possibly you're watching this video on your mobile, these are all computation which are carried by the rules using of classical physics. What do I mean by classical physics? This one, that information is stored in bits that are represented logically by 0 or 1, and the data processing is carried out by logic and sequential order. Right. So this is, I would say, a kind of an basic definition, or what was going on before the arrival of quantum computer, that it was logical, it used to store data in bits and bytes, 0 and 1, and it used to carry on the laws of classical physics and logic and in sequential order. Okay, so with the advent of these people, Dirac, Born, and the great Richard Feynman, for many years the fields of quantum mechanics and computer science formed their own distinct academic communities. Computers obviously played a major role in wartime cryptography, and quantum physics was essential for the nuclear physics used in the Manhattan Project. Now, as you see these people coming in, Schrodinger's and others, physicists applied quantum mechanical models to computational problems and swapped digital bits or qubits, and the fields of quantum mechanics and computer science began to converge, and the basic aim was this one: harness the entire power of quantum mechanics. Now, I'm not going into details into the architectural part, that how a quantum computer is basically being formed, but let us understand for the time being, because it would be too complex and too lengthy, that these people, when they started, starting with Albert Einstein and Max Planck, when we started development of quantum physics as a whole, there was also an inclination in developing quantum computation with the use and mathematics and principles of quantum physics. Okay, so we come to this person in 1980. Paul Binoff introduced the quantum Turing machine, which uses quantum theory to describe, I would say, simplified computer. When digital computers became faster, physicists faced an exponential increase in overhead when simulating quantum dynamics. And it brought this great person, along with Yuri Manin, Richard Feynman's, as you can see the paper, independently suggested that hardware based on quantum phenomena might more be efficient in quantum simulation. So you see, it started with Paul Binoff, and then Richard Feynman in this paper, Simulating Physics with Computers, have laid down a kind of an algorithm, an idea that yes, we can create quantum computation, and this quantum computation would not only help in physics and mathematics, but in biology, in healthcare, and in other sectors. We will look into that. Now, this was basically, I would say, spearheaded by Richard Feynman. It was done. Then in 1984, the paper of Charles Bennett and Gilles Brassard applied quantum theory to cryptography protocols and demonstrated that quantum key distribution could enhance information security. Now, I mean to say, these Paul Binoff, Feynman, Charles Bennett, and Brassard's algorithms did not actually solve practical problems, but it actually demonstrated mathematically that one could get more information by querying a black box. I mean to say, a black box is a system which can be viewed in terms of inputs and outputs with a quantum state in superposition, sometimes referred to as quantum parallelism. Okay, so these people, what they did is that they understood that if we use the principles of quantum mechanics, harness the power of the subatomic realm of physics, then we can get into something which is far more formidable, far more faster, and far more efficient. So with the quantum state, especially using superposition and entanglement, as we will see, it is called quantum parallelism. That means parallelly two things are occurring each other. Well, that is in short, I would say, an account of the development of quantum computers, although the history goes on for a long period of time. Now, the question remains that how do they work? I mean to say, quantum computers, they are fast, they are super excellent, but how do they work? Let us see in the next part of our video. Okay, so you see that if we take a kind of a classical computer, now I mean to say classical means they work classically. It is not necessarily, it has to be a old desktop with floppy, even the laptop that you are using or the telephone. Now here what happens is that the information is basically stored in bits and further into bytes. So all this information on the right hand side of your screen, Facebook, Instagram, YouTube, this video, all the multimedia information that we see are actually fundamentally stored in bits and bytes. We are talking of classical computer in order to see that from classical how we emerge and we graduate to quantum computer. So you see this letter A, B, C, every sound, every light, every kind of phenomena, activities are actually stored into 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? So this are the bits and bytes, and they move on and they get something like a kilobyte to megabyte to gigabyte and so on. And these things we are quite familiar of. So you see now what I'm trying to tell is that this information is the classical information which is stored in terms of bits. So bits means either it has to be 0 or 1. Remember carefully that this part is important, that it has only two possible states. That means an information getting inside a classical computer can be interpreted as any one. It can be either 0 or 1. Now herein comes the difference with quantum computing. This is an image of qubits that is like a blotched sphere. I'm not going into that. You ignore the psi and theta and other signs. Now in qubit what happens is that the value depends on the superposition of 0 and 1. What does that mean? That means that they can be in both the states. So there is an and nor an or. And this is basically what we call a coherent superposition. Coherent superposition in the sense that if the value of a particular data or an information is stored in both the states, that means both 0 and 1, then obviously the quantum computer behaves in a totally different fashion. That means if I take a data and knock the door of 0 and then knock the door of 1, you can understand the time it is taken to knock each and every door. Whereas if I knock both the doors of 0 and 1, the probability or the opportunity opens up all at once the two doors. So from here, I think you get a intuitive kind of an understanding that why quantum computer using qubits, where the values are in both the states, actually generates faster data. How it generates, let us look into the next part of our video. Okay, I will give you a basic kind of an idea that when we are flipping a coin, I cannot show the animation here, but when we are flipping a coin, when the coin is rotating, I mean to say we flipped and it starts rotating, the coin is in a superposition of being into head and tail. Remember, until it is falling down, it is both in head and tail. Now, as soon as the point or the coin falls down or reaches a state, it is either 0 or 1, or H and T, heads or tails. And this is exactly how the bits behave. If you have gone to my earlier videos in quantum mechanics, which is there in Physics for Students in my channel, the playlist of quantum mechanics, you will see that I have explained this superposition and other things in much detail. However, here what we need to understand that if the coin is rotating, it is in superposition, both head and tails. As soon as it stops, it attains one particular position, which is head or tail. That means it is similar to the bit. It is either 0 or 1. Now you see, it is a classical versus quantum bits. In classical, we have got 20 reds and 20 blue bits equal to 0, 1, and 20 reds equal to 0. Quantum bits, it is 8 upon 20 of 0 and 12 upon 20 of 1. So further you see this black and white, the empty is 0 and the bit is filled up 1. But in quantum, we say 1/3 of 0 and 2/3 of 1. Further, we see here a head and tail. There's a 50% chance of landing on 0 and 50% chance of landing on 1. So what we can say from here is the ability of a quantum state to be in multiple states at the same time until it is measured. Now, what do I mean by until it is measured? If you know about what is called a wave collapse or the quantum wave function collapsing, that means as soon as we observe, things fall down. We'll come to that part later, but this is important, that this is the superposition principle. Question is that how do we we will look into that. But further, I would like to explain a little bit about the superposition part. So if we take this subatomic particle, an electron is simultaneously in all the locations covered by its wave function. And from here we get probability density, Max Born's statistics. I'm not going to that. So here are two balls, blue one, 0 and 1. So in a classical system, it can be either outside the box or inside the box. But see, in a quantum system, it is 0 plus 1. That it means it is present both inside and outside. And this is very counterintuitive. So here is an example. Flipping the coin, when it is moving, it is both in head and tail. But when it falls down, we say it is either head or tail. And this is being explained in a very famous thought experiment by the great German physicist Erwin Schrödinger, and we call it a Schrödinger's cat. Don't worry, we will cover up Schrödinger's cat and its interpretation of how it helps in quantum computing. Okay, so you see there is something also which is called a wave-particle duality. That means the particle as well as wave. And we know that J.J. Thomson actually won the Nobel Prize in Physics for proving electrons are particles. Few years later, his son George Paget Thomson in 1937 proved that electrons are waves. You see that father is proving electrons are particles and son is proving electrons are waves. The question is that which one is true? And the answer is both of them are true. And this is something where every particle or quantum entity may be described as either a particle or a wave. Our dear old Dr. Albert Einstein was not at all happy, and this is the statement that he made. We have two contradictory pictures of reality, separating. Neither of them fully explains the phenomena of light, but together they do. I know this is not a video of physics and explaining wave-particle duality, but in due course of time, because we are dealing with quantum computing, a little bit of understanding of wave-particle duality is better. Okay, now here we come to something very interesting. We will see a quick note on what is the difference between classical computer and quantum computer, and then only we can understand the power of quantum computer. So you see, a classical computer is large-scale multipurpose computer, whereas quantum computers, they use high-speed quantum mechanics-based computers. Here you see the most important is that information is stored in bits, and whenever it is stored in bits, we get either one of the possibilities, but information here is stored in qubits, multiple states. We will come and explain to that. There are discrete numbers, obviously 0 and 1, and there are infinite continuous numbers of possible states. Now the calculations are deterministic, meaning that repeating the same results deals into same in output, but here it is probabilistic. It means there are multiple possible outputs to the same input. The data processing is carried out by logic or in sequential order, but here data processing is carried by quantum logic at parallel instances. This uses classical physics, and quantum computers uses circuit behavior and defined by quantum physics. This is mostly guided, those who know Boolean algebra, quite easy, and this is done by linear algebra because it gives a linear composition of the superposition, and it uses Hilbert spaces. Okay, so these are few of the differences, and now it is in front of you so you understand how both of them are different. But in order to understand further between how a quantum computer operates, we need to understand this very important: superposition and quantum computer. Before going into that, first let us understand fundamentally what is the superposition. Now, quantum superposition is basically understand that it is not a bizarre phenomena. I would say it is a fundamental principle of quantum mechanics. Now, in classical mechanics, things like position or momentum are always well defined. We may not know what they are at any given time, but that is in our understanding of the physical system. In quantum mechanics, a particle can be in a superposition of different states. It can be in two places at different time. So if I take classical physics in one way, we can say that things are quite well defined. The nature of the system is guided by deterministic mode, and the outcome is either zero or one. This is the basic tenet, the basic definition how classical system takes place, and that is how the classical computer also operates in this way. Now here is a catch. Don't worry about this horizontal and the angular bracket. This is called a bra and a cat notation. I'm not going to go into that. I have made 2-3 good videos on bra and cat. You can go to quantum mechanics and see on that. So now what I would like to tell you is that the quantum state, or the basis of states 0 and 1, these are called Dirac notation, right? Now what I'm trying to show you over here is that the quantum state, that it is always gives the result 0 in classical physics. I would say this is an AND, right? So 0 AND. But when we give the result 0 when converted to classical logic, it will eventually lead to 0 in measurement. Likewise, 1 will always give 1. That likewise 1 is the state that will always convert to 1. Now only thing is that contrary to a classical bit that can only be in the state corresponding to 0 or the state corresponding to 1, a qubit can be in multiple states. And that is being actually expressed over here. This is the famous kind of a Schrodinger's cat, where this equation is not the actual equation. This is just a kind of a, I would say, illustration given. It actually shows that the cat is simultaneously alive and dead. That means you see that when we are getting the result from the quantum to the classical state, obviously it cannot be random. Otherwise, how will we measure? But the thing is that when 0 is being converted to 0, I mean to say classically, 1 is being converted to obviously 1. But only thing is that in classical bit, that can be only in the state corresponding to 0 or the state corresponding to 1. And here qubit, which is the fundamental quantum bit, which is the fundamental particle we are dealing for quantum computing, can be in a superposition of both the states. This is very important. So now comes the most important part, is that we understood superposition. That means when we are measuring something, it can be in both the states. But how it is useful to come to quantum computers, let us say in this part of the video. Okay, I will take two states, right? Let us say qubits or bits, anything that you can imagine, one in a classical and one in a quantum computer state. So what I do is that if we do, then we get 1, 2, 3 and 4 states, right? 0, 0, 0, 1, 1, 0 and 1, 1. Now if I take further, say for example, classical computer, then what it will do, it is that it will process the data one at a time. First goes to 0, if not yes, then goes to 0, if not no, then it goes to 0, if not no, then it goes to 1. In this way it carries on and carries on until and unless it has find out the result. Now what does the quantum computer does? Does it does something really, I would say, weird? No. Quantum computer also takes 1, 2, 3 and 4. But the difference is that it will process the data all at a time. So you see the difference. Obviously when you're knocking all the doors and opening up quickly, then you can know on which door your friend is standing, either the first, the second or the third. But if you're going in a classical way, then you have to knock the first and then the second, and obviously then you can possibly find out the person in the third. So you see, if I take 3 qubits, it takes 1, 2, 3, 4, 5 and 6 states. And all of these 6 states, if a quantum computer is operating at a time, then you see and understand how fast and how efficient it would be. Further to that, if I take 4 states, right, it will eventually give into this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right? And the quantum computer is going to process all the 16 states simultaneously. So this is a kind of a pictorial description in order to make you understand that how the quantum computers, they don't do anything. I won't say they won't produce 5 out of 4 states. They would produce the same, but they would process it simultaneously. Now, if we take something like 2 to the power 64 qubits, it gives a kind of this kind of a monstrous possibilities. And this is something which is called 1 million terabytes. That's a good amount of data. And if we take something like a normal average laptop or a computer, which is called 2 gigahertz. Now, let me tell you a little bit what actually gigahertz means. Otherwise, you won't be able to relate to that. So hertz means actually times per second, right? And giga is basically a prefix that means a billion. So when the term hertz is used with computers speed CPU processor, it is in reference to the number of clock cycles. That means the data in which goes. So 2 gigahertz processor completes a clock cycle of 2.5 billion times per second. So the data, if it is going in 2.5 billion times per second, and for 2 to the power 64 qubits, will take around 400 years to complete. That is the problem or limitation of classical computers, right? So you see that with 2 to the power 53 that we sometimes call, that is the it has got 1, and you can count it. I think it is 1 after 16 zeros possibilities. And this Google claim with the Sycamore chip, they will be processing in data in 3 minutes 20 seconds. Whereas the Summit supercomputer will take 10,000 years. We really don't know, but that was the debate. So anyway, the basic thing that we need to understand is that this actually grows exponentially. The number of qubits that we are adding compared to normal Summit supercomputer, anything which is classically used, will take a huge time. Why? Because it will process one by one. Here it will process all and take the superpositions. I wouldn't say all at a time, but taking superposition as it sounds when we are talking is so easy, but actually in quantum computing it is not. And not only that, it is not only that we take a superposition, but we need something else coming up in the next part of the video, which our dear old Dr. Einstein called spooky action at a distance, coming up in the next part of the video. So here we see something which is called quantum entanglement, and it is definitely going to serve as the future of computation. Now it is a bizarre, I would say counterintuitive phenomena that explains how two subatomic particles can be intimately linked to each other, even if it's separated by billions of light years. So it is so, the definition says is a phenomena where we can say that the quantum state of each particle of the group cannot be described independently. That means one is entangled in relation with each other, right? Including when the particles are separated by large distance. So let us see that these two particles are separated, I mean to say, in huge distance. Now, let us say, for example, something like it can be billions of light years, right? But they're perfectly correlated to each other. What does that mean is that when two particles link up in this way, no matter how far they are separated, the states remain linked. So that means they share a common unified quantum state. The observations of one of the particles will automatically provide information about the other entangled particles regardless of the distance, and any action of these particles will invariably impact into the other entangled particle. This was actually studied in 1935 by Albert Einstein, Boris Podolsky and Nathan Rosen, who published a paper in the counterintuitive predictions that is called the EPR paradox of quantum mechanics. And in this study, the three formulated the EPR paradox, and they told that the quantum mechanical description of physical entity given by the wave functions is not complete. So if you see the paper cutting, it says that Albert Einstein attacks quantum mechanics. Anyway, so quantum entanglement is super important. We understood why quantum superposition is important, so that it can actually operate or compute in multiple fashion, because that is the basic tenet of quantum superposition, that a particle will be in two states. So if you take 2 and 4 and 6, the number of possibilities increase, the speed of the computer will increase. But also they are entangled with each other. Okay, let us take a quick kind of an understanding further. Let us say we have two entangled balls, right? Each in its own box. And in this metaphor, the balls, I would say, can be either yellow or red once observed. But for now, it is in a superposition of both yellow and red. Now here you see the object remains connected even over vast distances. So here it says mine is yellow, and even they say mine is red and mine is red. But what happens in this case if an observer decides to look at their ball from a different angle or a side of the box? You see that lady is trying to look at it in a different angle. The ball here, this lady, right? Here what will happen, the balls would revert back to the state of the superposition and have a 50% chance of being yellow and 50% chance of being red. Now you see, if I take this one, yeah, so here you see that what the ball was just red and it has turned to be yellow. Now let us take another case, and the viewer, what happens is that the viewer here, right, the second observer is trying to view the ball from a different angle, and what would happen is that it will match with the observation of the first observer. If you go back, you will see here the first observer, that girl, has seen it from red to yellow because it is seeing from different angle. This one turned yellow. So if the girl is seeing it as yellow, in the second case, the boy, this boy will also see it in yellow, right? So the viewers might find a yellow ball now, even though the pair of balls had previously been red. The reason it does, the balls are still entangled, but the viewer sees depend on how they look at the ball. The reason is quite clear. The reason is the entangled information about the color does not lie on the ball, but it exists between the connection of the balls. This is very important. So you see, there's this quantum entanglement that we understood the physics. Now if we apply to quantum computing, we will take two qubits, right, and we will connect with each other. So they are entangled from this part to this part, and this entangle, as you can understand, enhances the speed. Now why it enhances the speed is because before sending one information on the other front is already there. And this is something which we call condensed coding, and we are super condensed coding, and that will increase the quantum computing phenomena level. The question is that how quantum entanglement improves the computation speed of a quantum computer. That is what we are going to deal in the next part of the video. So remember, the next video is going to be more interesting than that, because we are not only going to look into quantum entanglement, but the future of artificial intelligence, the problems of quantum decoherence, how we keep the quantum computer physically, all those things. So here is a time to quickly summarize. So we learned that quantum computing uses the principles of quantum mechanics. It solves much more complex problems than the existing classical system. Digital computer, because they have two states, they are slow compared to that of quantum computer. And the advantages we learned, how we have we achieved quantum supremacy, the Sycamore processor which Google claimed, how quantum computers evolved. We also saw bits and qubits and principle of superposition. It actually helps us in developing and understanding quantum computing, because the number of possibilities operates are more at a time. How superposition improves the speed of computation, and quantum entanglements and its impact on the speed, but not yet done. We will cover up in the next part of the video. So this part is I am taking a pause here, and I would like to thank you for watching. Please do subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. As I always reply to my emails, you can write me to this email ID. You can also subscribe to my other channel which is exclusive to general theory of relativity, and you can follow me further on my Instagram, Facebook or LinkedIn pages. Thank you for watching this video. I will wait for your comments, and coming up next is the second part of quantum computing. Till then, goodbye.